So day 1, it says statistics 6-4, it says confidence intervals for variance and standard deviation. And let's face it, isn't that the one stat we really haven't done an interval for yet? We did the mean, we did p with p hat, but we haven't done it for sigma yet, right? We've done confidence intervals for everything else. And so that's what we're going to focus on today. Would anybody like to try and pronounce that first part? It says something dash square distribution. Yes. It's not chi. Nope. It's chi. Okay. It's Greek. It's chi. And one of the symbols for that, it may look very different, is it's one of like almost an italicized X is a way of drawing chi. And of course, instead of writing chi squared, we'll just do something like that. Don't you agree? That's chi squared distribution, right? Because we're kind of lazy, and so we're going to do that. It does rhyme with pi, right? So chi squared. Okay. And so I think we can agree with this statement. In many situations, it's important to control how much something varies, especially in production or various businesses. It's very important, supply and demand. If we can kind of control some of that or know how that's going to go, we're going to be much better off. And the chi-squared distribution helps construct those intervals for us for variance and standard deviation. And we're going to eventually do this same thing that we've been doing. We're going to find some point estimate for it, and then we're going to go one way, plus or minus some error, and that's going to be our interval. So that part really doesn't change. How we get there does. Getting that actual confidence interval is a little bit complicated, and so that's why we're going to save that for tomorrow. Today we're just going to hopefully understand the chi-square distribution. Okay. Here are various ones. Mine are colored. You might have to draw some arrows on there for yours. So, and you have NU on yours, right? That's just degrees of freedom. So degrees of freedom equaling 5 is the blue one. So for me, it's this very first one here. So you see that and you notice these probabilities are very tiny, right? Look at these probabilities on the left. They're so small. And so make a little arrow that this is degrees of freedom 5. Remember, that's the number of things out there that are allowed to be whatever. Okay, so there's 5 degrees of freedom out there. This is also n-1 to find degrees of freedom. Okay, so it's the same idea. So you might want to just draw an arrow over there. And you notice as the degrees of freedom get bigger, what happens? It becomes wider and becomes more and more bell-shaped, so more and more evenly distributed or normally distributed. Very good. And so when the degrees of freedom are very small, it's very front-loaded. Does that make sense how I said that? And then it tails off. The area underneath any one of these is 1. Okay, but you notice sometimes it's very front-loaded there. What did I put in there for? Oh, I put important stuff in there, so that's good. And did I take that off on yours? No. Underneath there, you see that it says chi-squared equals n-1 times s squared over sigma squared, right? I don't think I have that on mine unless it's on the next page. Let's just take a quick peek. No, I don't. So the actual distribution is n-1. We've seen that before, right? Standing for, in most cases, degrees of freedom, right? Because that last one kind of has to get you to the right answer, right? So the other ones can be whatever they want, but that last one. Now, s squared, what's that again? Sample. Nope. That'd be just S. Would be sample standard deviation. So that's sample. Starts with a V. Variance. Okay. And we're comparing it to sigma squared, which is what? Nope. Not standard deviation. Not if it's squared. Variation of what? Population. So we're comparing basically our samples variance to the population. And let's face it, don't we kind of want that to be really, really close? So wouldn't we like s squared over sigma squared to be very close to what number? 1, right? And so we're basically just multiplying by some degrees of freedom, if you look at it that way, right? And so hopefully we can get those two as close as possible, but if our sample size is very small, is that a very good chance? No, which is why you see not very normal when degrees of freedom are very small. But as degrees of freedom get better, and that's more data, so should the two get closer and closer? So doesn't that kind of make sense? But here's the hard part. Look at these values on the bottom. Look at how far over they go. So the better you get, right? Here's your sample size, really, right? So the bigger you get, the further over it pushes it. Does that make sense with that distribution? Well, yeah. The more bigger number I put in for n, the closer s squared is going to be to sigma squared. And so the further over it's going to go. So here are some very important properties to the chi-squared distribution. We've talked about some of them already. First one, the mean of the x, or the chi-squared distribution, will equal the degrees of freedom. What? What does that mean? Anybody kind of put that in regular person words? So the mean of the chi-squared distribution will equal the degrees of freedom. And your book kind of fails to mention these properties, so I think it's kind of, well, the book you don't ever see, but the book we have doesn't mention this. So let's just take one of them, for example, up here, because I just showed you various graphs. Right? You might get a problem where the degrees of freedom is 21. You never know, right? But that's why you have a table. So let's just look at maybe the blue one up here, the degrees of freedom being 5. Everybody see the blue graph there? Look what's kind of in the middle. Not quite. Well, we might as well use blue, huh, if we're going to do blue. Do you agree about 50% of it's going to be over here and about 50% of it be over there? Because remember, this thing's just going to keep going to the right, right? And so it's saying that the mean of your distribution is going to kind of be in the middle. So let's maybe do another one. Let's do degrees of freedom 29, which is this very last one. And do you see that 29, and maybe we'll do black this time. 29 is right about, what, there? 50% that way, 50% that way? So is this a perfect normal distribution? But is it getting closer and closer the further we go? It's getting better and better, isn't it? So you can imagine we start talking degrees of freedom 100, well, we're almost going to be sitting there perfect at a normal distribution. Okay? And that's really the goal here anyways. All right? So what we have to be able to find out are these values on the bottom. You know, what are they exactly? Because it's not going to be perfect every time. All right? So that's what that means. This is an interesting one that they sometimes kind of fail to mention in a lot of textbooks. So what's sigma squared again? Yeah, population variance is going to be very close to equal 2 times the degrees of freedom. So in other words, variance gets bigger as degrees of freedom gets bigger. Isn't that kind of what it's saying? Does that also hold true in our graphs? Does the variance get bigger as the degrees of freedom get bigger with our graphs? It doesn't, spreads out, doesn't it? But isn't that kind of what we want it to do? So that's okay. We'll let that happen. Okay? We're not going to fight it. We'll just let that happen. I think we knew this one. We already said this one, right? As the degrees of freedom increase, it gets very, very close to the normal distribution. In fact, is there another line there? Yep. It seemed weird that that statement would end with the word normal. It approaches the normal. Okay, so those are some pretty good properties right there. The key is to realize that the probabilities are really tiny. If you look at the left, very tiny. And once again, if we go back to the distribution, it's basically what we find in our sample versus what we're supposed to find in our sample, right? Really? What we find versus what we're supposed to find. That's the whole idea of chi-squared. Okay? What do we find versus what are we supposed to find? Everybody good? All right. So what I've done is I've taken the liberty of using the TI-83, which can graph these quite nicely for you if you know how. And I had it graph this particular example for us. So if you had to look at this graph without even reading the question, what would you guess degrees of freedom? If you had to take a guess, would you guess 12? Would you guess 2? What would you say for degrees of freedom if you know the degrees of freedom is supposed to equal the mean of your distribution? What would you say about the mean of this thing is? Because we're going 50 on the left, 50 on the right. I've heard 6 or 7-ish. You think somewhere over there, right? 6, 7 in here. If I drew a line up, do you think 50 to the left, 50 to the right? Yeah, what if I chose like 2? 50 to the left? No. What if I chose 12? No. 6 or 7, you think? Yeah, maybe something in there, right? Maybe even 5. Again, I want you to kind of look at these things conceptually as well instead of just reading the problems all the time, okay? But that's about where you figure out. Does this seem like a very big variance here? Not too bad, right? The standard deviation's not huge here, right? Maybe a couple, right? All right, so suppose I knew that the standard deviation on a particular test was 4 points. So maybe I gave you guys a test, or maybe it was that basket weaving class I had. I gave them a test, and I knew the standard deviation for that entire test was 4 points. Let's say then I took a sample to see how good I could do sampling, and I took a sample of 7 tests. Okay. Notice, did we say anything about n on this one? Not really. We didn't say n had to be 30 or anything like that. The standard deviation I calculated to be 6. So the sample I took varied more than the actual population. Calculate the chi-square statistic. Most people don't believe that that's actually a statistic. It's actually some number that comes from a sample. Okay. And then let's interpret that. Well, how are we going to calculate that? Well, we're going to use your little formula, which is a comparison of 2 numbers, because it's a ratio, right? It's really, if you look at it, is how good do those 2 compare to each other. And so we'll go ahead and we'll do that. So our chi-squared, now I actually want to know what chi-squared is. I don't want to know what just chi is, all right? So don't start taking square roots on me here, okay? So what is n in our problem? 7. Okay, so 7 minus 1, because again, let's face it, what is that? But what does it stand for? Degrees of freedom, right? Okay. And so S, where are we at for S? Which one of these? Now, how do you know which one's S and which one's sigma? That's kind of what we observed, right? We observed on the sample we took that the standard deviation was 6, and that's what S is, right? And what were we supposed to have seen? Yeah, 4 squared, right? So basically, if you look at it in a particular way, 6 cubed divided by 4 squared, right? If you look at it from a particular point of view. Okay, so why don't you figure out what is chi squared? Again, don't take a square root on me here. Just figure out chi squared. You can use a calculator, it's fine, you know. And has anybody come up with that number yet? 13 and a half. Now, look at your distribution, and look where 13 and a half would be. I gave you the picture, didn't I? Okay. So this is actually the picture for a chi-squared if you had 6 degrees of freedom. So the actual mean of this is 6. Okay. So whoever said 6, excellent job. So we know that if I went there, we're talking 50 and 50, right? Okay, and that's why I'm trying to get you to understand this better. Most books don't do that. They just say, oh, here's the stat, just figure it out. Well, that doesn't help you if you don't know what in the world you're doing, right? And so where does 13 and a half fall? Well, that's way over here, isn't it? 11, 12, 13, somewhere over in here, right? Now, does it make sense that I'm to the right of the mean? Well, the variance was supposed to be 4, and I'm at 6. So does it make sense that I'm to the right of it? I'm more than what it's supposed to be, right? So it doesn't make sense. And so what we're eventually going to do is we are eventually going, not today necessarily, but we're actually going to figure out what is this. But how many tails are we talking about with this particular problem? Just 1, okay? And eventually we will find that percentage. What percentage do you think that is? Shaded. Just take a guess. 93, you think? 95? It's actually 96. And you're going to learn how to calculate. Whoa, that's bad, but you get the idea. 96% is in there. So what that means is if I did this a bunch of times, I would expect my standard deviation to be 6 or less 96% of the time. Or more than 6, I would only expect that to happen 4% of the time. Now, does that make sense? If I did all my tests and I found the standard deviation was 4, would it be very likely to take a sample of just 7 and have the sample have that standard deviation be 6? Is that really possible? Yeah, it could happen. But is it very likely? Not really. But 96% of the time it's going to be less than that. Okay? Yes, questions? No, I got the 6 because remember the mean of a chi-squared distribution is equal to degrees of freedom. It will always happen that way. But you realize then as n gets bigger, that number gets further out as your mean, and that's why that whole thing just starts stretching out. Because what do we have? Last one was 29 we had on there, and it really was stretching out, right? So imagine what that looks like at 100. You know, that thing's huge, okay? And the graphing calculator will still do this. I just have to change the window because otherwise you wouldn't see it, right? Yes? Your variance will be, our variance basically, if you look at it that way, is 12. So you take the square root of 12, and that would be your standard deviations, how many standard deviations you'd have to go. We're not going to get that in depth yet. But remember, variance, they're saying, is it's basically 12 for this problem, right? And so the square root of that would tell you standard deviations. So am I quite a few standard deviations over to get to 13.5? Actually, yeah, I'm probably, what, about 2? So does that make sense, about 95-ish? It does. Is it going to be perfect? No. Okay. But again, remember, most books don't even give you this information. I don't know why. It's maybe they don't think you can handle it or something. But really, that's where that comes in. The question was, how about that second property? Well, yeah, variance is about 12 in that problem. So standard deviation is the square root of that. And so we're talking a couple standard deviations, which makes sense to be 90-some% then. But that's a one tail. When you do good testing, you're going to use two tails. Because it's one of those statements that says, at least as extreme as. Well, the extreme could be to the right, or the extreme could be to the left, okay? So this was a stat. I just wanted you to kind of understand what it looked like, how it worked, just in general, all right? And so now let's actually go and find what are called, those of you in calculus are going to love this, critical values. But this is a chi-squared critical value. All right, and that's where your table is going to come in handy. So take out your big table that you have, and you notice on the left it says DF, meaning degrees of freedom, right? And it goes, what, 1 to 100, but towards the end there it skips a bunch, right? And then you notice going across, you have 0.995, 0.996. Anything seems strange about this? Anything strange about how they're giving that to you? No, not what I was looking for, but it's getting... How about the top number is getting what as you go left to right? Smaller. But the bottom number is getting... Huh? So the top one's getting bigger, but the actual number in your table, or the top one's getting smaller where the actual number in your table is getting... Huh. Well, that's interesting, though, isn't it? That's because these numbers are saying, these numbers here are what percent do you have to the right of your critical value. So I have 99.5% to the right of my critical value. Okay? And so it'll make sense once we do one, I think. Explaining it before you do one's kind of difficult. So the previous example works great if it's a one-sided tail, but normally when testing you use two. And so we're going to find critical values, and we're going to name them. We're going to call it chi-squared right and chi-squared left. Because that last one, I would say we kind of just got one. We got 13.5, right? Well, now we're going to find more chi-squared right and chi-squared left. So here's the difference. Last one, we had 96% over there at, what, 13.5? But now what we're going to try and do is find two values. Maybe it's here and here, so that in there is, in this case, 95%, right? So we got to shift things a little bit, right? We don't want it to just be one tail. We got to shift it over a little bit. But now here's where reading the tables becomes increasingly more complicated. The table you have is giving you one tail numbers. All right, and so we're going to have to work with that. Okay? So we're going to use the information from example 1. Well, what information is important? Well, according to this table, what information is important? Degrees of freedom. And how many did we have? We had 6. All right. So let's just draw some little general graph here, and I'll draw you one. Let's say you look like that, right? We want to find a number here and a number there, so there we got 95%. But then how much is here? 2.5. How much is here? So can I just go find the number for 95%? Is that going to do that for me? No, what do I have to go find? 97.5, and then over here I have to find, no, 20, right? Over here you can just find 2.5, right? It's right there, just find 2.5. And over here we have to find 97.5. So that in between is actually 95%, right? Because 97.5 minus 2.5 is 95, right? Okay. I know it's Monday morning, little difficult there, huh? Okay. So here's how you read this table. So do you agree that I pulled up the right one? So sometimes I use a ruler or something, or maybe a folder when I look at mine. Okay, so maybe put something across so that degrees of freedom is 6 is the last one you can see. And so what we're going to do is we're going to say, well, we have to find 2.5, and we also have to find 97.5. Well, do you agree that right there is 97.5? And then right there is 2.5. Okay? All right. No, you just write them down. So which one is further to the right? Well, that one is, isn't it? 14.449. Because you agree this is the one on the right, and this is the one on the left, right? But here's where this one's tricky. It's saying what percent is to the right of it. That's why this one's so weird. Okay? And so I'm going to try and make it easier for you. And do you see how they've inverted it? So this one actually is to the right, and this one actually is to the left for you. And you can just write it down. They were very nice how they made this table. They didn't have to be. They were incredibly nice to you. So here's why this looks weird. This is saying that there's 2.5% to the right of that critical value. Do you agree with that? But you see how far over I had to go to get that to happen? And this is saying how much is to the right of this one. They're saying 97.5% to the right of that one. Okay, so that's why this one's all backwards. But do you agree if I go right there? Okay, so that's why this distribution's weird. It gives you the area to the right instead of the area to the left, which was what every single other one has done for us. So what it's saying is if I go here, what's this, 1 point, about there, all the way over to 10, 11, 12, 13, 14, wait, 10, 11, 12, 13, 14.5. They're saying if I go between there, we're dealing with 95%, which means over here, 0.5%, over there, 2.5%. But what it's saying is if I go from 1.237 going that way, I've got 97.5% of the data. That's why this one's different. And this one's saying if I go to the right, I only have 2.5. What do you mean 0.9 and 0.1? This is saying 90% is to the right. This is saying only 10% is to the right. Okay, so 90% to the right would be somewhere over here. Okay, 10% to the right would be way over here. That's why there's such a huge jump from 2.204 to 10 point something. Because remember, the mean of this thing is 6. Okay, and standard deviation's square root of 12, whatever that ends up being, right? So 3 point whatever. Okay, so that's why chi-squared is so weird. But they set up the table so that if you just look to the one on the left and look, you're good. Because let's face it, you're going to be able to find these two numbers, 97.5 and 2.5. You'll be able to figure that out, and then it just gives it to you. Okay? So it is kind of weird. Do you think you can handle that? Well, we're going to find out. So let's say I gave you a slightly different one, and why don't you find the same setup, so 6 degrees of freedom for me, but find, and let's say I gave you a sample of, not sure what I meant by that. Well, I think it's a sample of, we'll say 20. So just find that. So I'm giving you a 90% confidence interval and have a sample of size 20. Can you go get the critical values for me? So sample of 20 and 90% confidence. So go find chi-squared right, chi-squared left. No, what is degrees of freedom? 19 degrees of freedom. Okay. Yep, 90%. And while you work on that, I'll bring up the entire table. So what degrees of freedom are you looking at? 19. So these are the numbers you're referring to here, right? You agree with that? So if 90%, you have to have 90% in the middle. So what's going to be, how far you got to go over? It's 95 and go over to 5, right? Because 95 minus 5 is your 90%, right? Okay, so which of these numbers going along is that one? So is this 6.84? Is that? No. How about the 7.633? No. How about the 8.907? Not yet. 10.117? Is that one of your lower numbers? So that's chi-squared left. Okay. So it goes what, 4 in? So 1, 2, 3. So it's 30.144 is chi-squared right. Chi-squared right will always be bigger than chi-squared left because it's a number line going left to right. But you see how they inverted everything for you? Oh, well, you're glad they did, trust me. Where this goes next, you're glad they inverted it for you. It makes life a lot easier. Okay. So it would be from 10.117 to 30.114. So how come that's such a bigger number? How come? Why does that work that way? Yeah, exactly. Your graph is way more spread out like this, right? And your mean's probably a little bit still over here, right? Your mean is 19, right? So you got 50% that way, 50% that way. And what else also got bigger? Degrees of freedom got bigger, which in this case made wider, which means your variance and standard deviation got bigger. Okay, so it got out there quite a ways. So we went all the way out to, what was it, 30 point something? 144, all the way over to 10.117. And what's in here then? 90%. Okay. So what we're going to focus on most on your assignment today is finding those critical values off your table. Because if you can't get chi-squared right and chi-squared left, there's no sense going on to getting the confidence interval. Okay? Do you think you can do it? All right.